Hello, everybody. Today we will discuss about stress and deformation that are caused by torsion. This lecture is a part of a thought course of mechanics of materials for international program in civil engineering at King Mongkut University of Technology, Thonburi. Thank you for being here with us. Before we begin with the mathematics and the calculation, let's look at the physical phenomenon of material under pure torsion. Right. As usual, if we look at the beam here, or maybe a column, it doesn't matter, just let's say a beam, right? If I subject a torsion, the torsion is actually a moment that going around an axis that going along the length of the member, right? In this case, in usually what we call is the x-axis. So this is the moment of x-axis, right? This way or this way, right? So if you look at the two lines here, as usual, it designates the two cross-sectional area. So if I do it like that, notice that the rubber here is twisting. It doesn't bend, it doesn't extend it, it's just twisted, right? Now, if you look at the cross-section behavior, it is almost like it's formed like that, it's just like this, right? It doesn't move away or into each other, no, it doesn't slide up or down, front or back, no, it's just rotating, right? But it's rubbing each other. So because it's rubbing each other, it's actually called the shear stress, and of course it becomes shear stress and shear strain because it's in a way it is definition of the shear is when it's rubbing each other, right? Now, if it's twisting, right? So we have to find a way to measure it, how it twists, right? The first one that I'd like to call your attention to is if I draw a line onto the length of the member here and I twist it, right? Notice that that line also, although remain a straight line apparently, is actually turning, right? Basically, it's changing the angle, right? This angle change along the length of the member. This is gamma. Is the one that we calculate as shear strain. However, there's another rotation that we should concern with is on the cross section here. If you see a line here, if I twist it, notice that the line will turn, right? So basically that is how we actually look at the cross section when it starts turning, because this is called angle twist, meaning this have the effect on how we feel the deformation. Is it big or is it small? Although I show what happened physically with the rubber, which has cross-sectional area of rectangles. In this course, we're going to look more in a circular shape cross-sectional area. So just to familiarize ourselves, let's look at this picture for a little bit. But the definition and the terminology will be the same, just changing from rectangle into a circular cross-sectional area. Now, if you look through the length, this is the front view and the cross-sectional view on the right-hand side. You can see that there are two kind of rotation as we already discussed. The one that's rotate along the length, the change of angle along the length of the member, and the change of the angle of the cross-sectional area, right, through the length defined by the shear strain gamma, and then on the cross-sectional area is the one that make us feel whether it's changed a lot or not, which is called the angle twist. Now, if we look at the cut there at the distance of x, then we should realize that if we project it back onto the new cross-sectional area, that gap between the red line and the blue line becomes smaller, right? Meaning the angle of the angle twist in the cross section here will have actually less value than the one in the end, right? In other words, in fact, it means that the angle twist is a function of a distance throughout the length of the member. So that's why it designated by phi x. Right. On the other hand, if we look on our way around, rather than looking through the length, then we look through the thickness of the tube itself, right? Meaning we look through the smaller radius and then peel the outer layer out, right? So we're gonna have to see a thinner one, right? Now this gamma here, let's look at the relationship between the gamma and phi for now, so that we can relate back later, right? If I designate the point AB, which is the arc length between the red and the blue line, which is the total rotation, right? Gamma will equal to AB over L, and then AB on the right hand side there will equal to phi times R, and then we take the ratio because AB are equal, and we swap things around. We can have relationship between gamma and phi as follow, as a ratio of radius and the length. Now back to where we discussing that we peel off the outer layer, then we see a thinner one, right? Now notice that the on the cross-section view now phi doesn't change because it's still the same angle as the one on the top, so it's still the same phi. However, because of the radius smaller, if you project back into the front view, the gap between the blue and the red is actually smaller, which means that even though phi is a function of x to the length of the member, the gamma, the shear strain, is actually a function of the thickness through the radius. Again, this radius measured from the center point of the circle. Right. If we use the same ratio with the top, then we can relate to the gamma and phi in the middle as well. Now, because these two can be relating to each other, we can have a ratio between gamma and R as follows. And of course, next, later on, I have to say later on, not next, but we can look at a smaller section. So we want to find the totality of everything. So we look through the thickness, and then we also look at small dx through within the length of the member as well. But before we move to that, let's talk about how we calculate the stress from the cross-sectional area first. Let me move the old board to the left-hand side, right, and begin the new board on the right-hand side here, right. Now, if we're going to consider the shear stress, don't forget that the shear stress relating to when we combine all the shear stress or cross-section, then we're going to get, in this case, torsion, because we don't have axial force here, we don't have bending moment here, right? We have only torsion. So what we think about here is the moment about x-axis. In this case, the x-axis will go into that dot in the center of the circle. It will go into or out of the board, of course, right? So if we designate a smaller area, dA, at any radius r, little r here, right? Then on that dA, we have a shear stress caused by torsion here, right, on that dA. And if we want to work out the total force, then of course it will equal to tau dA. And because torsion is a moment, not a force, we need a moment expression. But by the geometry, then the arm for that force dF is the little r, right? The smaller radius where the dA situated. So the total torsion caused by that small area here is equal to r dF or r tau dA per se, right? And we already have that relationship in before, right? We also know that the relationship between the shear stress and shear strain are linked by the G. G is the shear modulus of elasticity, right? So it's a real life function, which means that we can change the gamma into relationship of tau instead, right? Again, we will try to play around with it, and then we move on tau onto that ratio on the right hand side there. We will see why we need that, because we need that constant out of the integration, basically. Well, we see in a bit, right? So now, if we have expression of dt, substitute that expression for tau into the expression, then we have r squared dA in that bracket there. Then if we want the total torsion, right, so we integrate total area, And of course, as I mentioned before, tau max is a constant. Big capital R is the total radius, is constant as well. So you can take out of the integration. And you should be familiar with this term here, distance square dA integrate over the area, that it tends to be area moment of inertia, right? However, this one here, because the way we measure, it's not about x, y, z, it's about polar coordinate. It's going around in a circle. So that is designated not I, but J, and it's called polar area moment of inertia. Substitute that back into the equation to shorten it, swap for equation so that we can find tau, and then we have these two expressions to contend with. One for stress, shear stress caused by torsion, and one is for the polar area moment of inertia, J. Before we move on, let's look at how we calculate or how we determine the polar coordinate of inertia for a circular cross-section like this. So let's look at not any particular cross-sectional area, just radius r, right? So if we set up xy, well, we can integrate, but it's a little bit difficult. So I have to go into the polar coordinate system as it is intended to be, like that. Right. So rather than just having a box, then I create a ring, dA. Right. That ring, of course, will be with the same radius away from the center, the letter r, right? Which means that the length of the ring will be circumferences 2 pi r as usual. And if you want the total dA, then you times the thickness dA, right? Sorry, the r. So here we are. This is the expression for the polar area moment of inertia. dA I explained already. Circumferences times the thickness dr. Then substitute into it, and then, well, in simple integration, then we have the r to the fourth pi r to the fourth over 2, and that will be the expression for the polar area moment of inertia for the circular area. Now let's look at how we calculate the angle twist. We go back to the last picture we draw before we move on to the stress. This is where we look at the thinner layer of the tube, and we also look at the little cut dx in the length of the member. I will expand that dx a little bit so that, well, a lot, so we can see it clearer, right? So basically, in fact we should see only the red line, the full red line, and the blue line, right? However, that doesn't represent the change between the left-hand side of dx and the right-hand side of dx. So I draw a dotted line. So that gap there between the red dotted line and the blue line on the right-hand side is actually what actually changed between the beginning of the x and the end of the x. So basically, if I draw a cross-sectional area on the right-hand side, I will see only the red line and the dotted line, right? Now, if we look at the right-hand side, then we're going to see actually the full red line and the full blue line, right? But how I would draw the dotted line as a reference on that is the change. So basically, between the full red line to the half red line, the dotted red line is the original phi from the left-hand side. But then once it moved through the x, the angle change, and that change in angle on the cross section is denoted by d phi. Before we move on, I'd like to talk about the arc length here because it will be relating to what we're going to calculate next. If I designate point A at the blue line on the arc, right, at the blue line, blue dot there, and then B from there. Notice that the AB, although happen on the two different points, is actually the same arc length there. Right? So if I calculate this arc length on the dx side, the AB equal to tau dx. Oh, sorry, gamma dx. My apology. But if I look at the right-hand side here, I will have AB is equal to r times d phi. Right. However, these are the same AB, therefore gamma dx must be equal to r d phi, of course. Right. And we can swap things around because we want to find the angle twist. It would be useful if we have d phi on the left-hand side and the rest is on the right-hand side. Now, we already know the relationship between shear strain and shear stress. So we can actually substitute so that we can talk about the shear stress, but which we know the expression. And here is the expression. And if we substitute that into the expression for the phi, notice now, then we have terms that we can calculate directly in the phi integration. Torsion will come from free body diagram. Polar area moment of inertia will come from the cross-sectional area, right, which we already proved for the circular cross-sectional area. G is the material property, which is the shear modulus of elasticity. So we can have that before we need to know anything. So it's going to be easier for us to do it this way rather than calculate for stress first, right? So in a way, there we are. And if we want to know the total one, then we can integrate from point A to point B. Let's say if it's length L, then it's from 0 to L. And if usually the case, J and G are constant, and if torsion happen to be constant over that length as well, then we have simple expression as shown here. So let's summarize what we have done so far. We have expression for shear stress caused by torsion, tau. We have the expression to calculate the polar area moment of inertia for the circular cross-section area, J. And we also have the formulation to calculate angle twist, especially useful if the torsion, the polar area moment of the shear, and the shear modulus of elasticity is constant all over that length. Then it's simple, and we don't have to integrate it. Let's look at an example. Just a beam getting out of the fixed support, right? Two torsion apply on it, right? Two places. And then the question is if this cross-section area drawn on the right-hand side is actually at point 3, I emphasize at point 3, but it's constant all over the length anyway, right? But at point 3 here, there are 2 points that they are concerned with, that they want to know the stress, and then they also want to know the total angle twist until the end, point 4. Here is the equations concerning us. Well, as usual, I like to starting off with the forces or moment side of thing, in this case moment, of course. So we start with the free body diagram, right? This is torsion. So basically this is anything, that moment here is all about x-axis. So one unknown, one equation, right? Simple. Then we can take the moment and then calculate it. And then if we want to know the torsional inside between 1 and 2, then we cut somewhere in between them, right? Not in the middle, not any possible space between them, right? And we calculate torsion between 1 and 2. And between 2 and 4, the torsion will be consistent because there's nothing in between. So here we are, and we can calculate the torsion between 2 and 4. The area itself, simple enough, right? Because we have the expression, we just use it and calculate the polar area moment of inertia. Notice one thing though, although we have 2 points to contend with, one is at a radius of 3, one is a radius of 2 centimeters. However, the J, the moment area of inertia, similar to I, still be calculated from the total area, not divided the area before your calculation. Okay, the area moment of inertia in mechanics tend to be total area. And then because torsion at point 3 is between 2 and 4, which is a constant at 40, so we use the same one. Now notice that tau at point A and point B in the calculation, all numbers will be the same. The one that's different is the radius, because that is the only thing that's different between them. Torsion the same, J the same. Again, we use the total J no matter where the point is on the cross section. Okay, for the same free body diagrams, we can calculate phi between 1 and 2, right, as follow. And I have to emphasize this between 1 and 2. It's not absolute yet, it's just between 1 and 2. And we also can calculate from between 2 and 4, right? Notice the way the phi goes and the torsion go. It always go the same way when you calculate relative one. This one here is relative. The first one on left hand side is between 1 and 2. The different between 1 and 2, 2 and 1, and the last one is different between 4 compared to 2. But it's not an absolute. How do we do it? Then we look at the support conditions, right? Because this beam here stuck at a fixed support at point 1, therefore at point 1 doesn't move, right? And then that point 2, phi 2, which is equal to phi at point 1 plus whatever change, 1 is 0, so it will be equal to phi 1, 2, of course. And after that, then whatever happened at 4 will equal to what already happened at 2 combined with what happened between 2 and 4. Right. However, this one here is opposite direction. At point 2 is already go positive x, whereas the between 2 and 4 is going negative x. Right. And therefore you use them to minus each other rather than plus each other, and we get angle twist at point 4, phi 4 as follow, and that's the answer. So I put answer into it. Okay, that's it for today, guys. I hope you enjoy learning with us and it have been helpful to you, and I really appreciate you guys being here. So thank you, and I hope to see you guys again soon. Goodbye for now.